Hi, we are going to discuss the rational zero theorem. So we don't really have a method that would allow us to solve polynomial equations. Like for example, for quadratic equations we have the quadratic formula, but for general polynomial equation we don't have a formula that would work all the time. And one of the things that we can do is using the rational zero theorem, we can identify possible rational zeros that you can then test, and you can see if any of them actually work. So how do we do it? Let's start with an easy case. If the leading coefficient is 1, then we're going to take a look at a constant term and find all its factors, list all its factors with both positive and negative signs. So our constant term here is -6. You can actually disregard the fact that it's negative because every number is going to be taken with a positive and negative anyway. None of the other things is going to matter. Doesn't matter what the degree is, doesn't matter how many terms you have, what the other coefficients are. The only thing that we care about is the constant term. So what are the factors of 6? It's going to be 1, it's going to be 2, it's going to be 3, and it's going to be 6. But we're going to take it with both positive and negative signs. So plus minus 1, plus minus 2, plus minus 3, and plus minus 6. These are our possible rational zeros. Does not mean that any of them will necessarily work, but if this polynomial here has a rational zero, then it's going to be at least one of these numbers. Let's do it with the next problem. So our constant here is 12. So what are the factors of 12? It's going to be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. So as far as making a list of possible rational zeros, this is all you do. But one thing that I want to point out here, the leading coefficient for both of these examples was 1, and that makes it easier. What if that number is not 1? Do you do the same thing? Actually, no. If the leading coefficient is not 1, you're going to have to write the ratio of the constant over the leading coefficient. You do not simplify that. You make a list of factors for each numerator and denominator, positives and negatives, and then you write the unique number that you're going to get. So the first thing that we're going to do here is we're going to write 6 over 2. Please remember, you cannot simplify that. It's going to have to remain like that. 6 is our constant, 2 is our leading term. The leading coefficient. So what are the factors of 6? The factors of 6 are plus minus 1, plus minus 2, plus minus 3, and plus and minus 6. What are the factors of 2 on the bottom? Plus minus 1, plus minus 2. And now we're going to take every possible combination and see what we're going to get. So we're going to do plus minus 1 over 1, plus minus 1 over 2, plus minus 2 over 1, plus minus 2 over 2, plus minus 3 over 1, plus minus 3 over 2, plus minus 6 over 1, and plus minus 6 over 2. Are you going to have that many? Well, we'll see. This is 1. 1 divided by 1 is 1, so plus minus 1. Done. Plus minus 1/2. Done. Plus minus 2 over 1 is 2. That's another one that we're going to have. Plus minus 2 divided by 2 is actually 1. We already have 1. We do not do it again. 3 over 1, a unique number. 3. 3 over 2. 6 over 1 is 6. And 6 over 2 is actually 3. We already have 3. We don't write that. So that would be our list of possible rational zeros. Let's try it with this example. So it's 12 over 4. 12 over 4, 12 has a lot of factors. Well, a lot more than 6. Plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. Right? Over plus minus 1, plus minus 2, plus minus 4. Because 4 has those factors. Now we're going to have to make, I don't want to write the same exact list that I did here. Let's just take a look. So 1 over 1 is 1. So we're going to have plus minus 1. Then you have 1 over 2, that's 1/2. And 1 over 4 is going to give us plus or minus 1/4. Now we switch to 2. So 2 over 1 is 2. So plus minus 2. 2 over 2 is 1. We already have 1. Don't do it again. 2 over 4 is 1/2. That's something we already have also. 3 over 1. It's plus or minus 3. 3 over 2. We don't have that yet. And 3 over 4. 4. Gonna have a lot of numbers. 4 over 1 is 4. We don't have this yet. 4 over 2 is 2. We already got 2. 4 over 4 is 1. We already have 1. 6. 6 over 1 is plus or minus 6. 6 over 2 is 3, which we already have. Don't need to do it again. 6 over 4 simplifies to 3/2. We already have that. 12 over 1 is 12. 12 over 2 is 6. We got that. 12 over 4 is 3. We got that. That is going to be our list of possible rational zeros. Okay. Again, this is just a list of zeros. Does not mean they are necessarily going to work. Okay. So, excuse me. What is the benefit? The benefit is, once you make a list of possible rational zeros, you can test it and see if any of these numbers are actually going to work. So what we're going to do here, we're going to take a look at these examples and try to find all rational zeros that this polynomial function has. So the leading coefficient is 1, makes it easy. The constant here is 42, so we're going to make all factors of 42. That's going to make our possible rational zeros. That's plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 7, plus minus 14, plus minus 21, and plus minus 42. Now, the question is, when students first learn this, which number do you start with? Well, to be honest, you don't know. You don't know which number is going to work. You're going to have to pick a number and go with it and see if it works. You may get lucky and pick the first number that's actually going to work. You may not get lucky and you may not get the number that works, because what we need to do is try synthetic division and see if we're getting 0 as a remainder. And if we get, that's great. If not, then we're going to have to keep trying. Usually we start with smaller numbers because, you know, it's not a very common thing that one of these high numbers is actually going to be the answer, but it is possible. So I don't know, let's pick 1. Does 1 work? So we're going to write our coefficients. We're going with synthetic division. And let's see, we bring down 1, that's 1, it's negative 5, that's negative 5, that's negative 18, it's negative 18, and we're getting here 24, not 0, nope. X equals 1, no, does not work. So, you know, you can keep trying. You can try negative 1, for example, next, or try another number. Let's go ahead and try 2. So if I try 2, 1, negative 6, negative 13, 42, 1, that's going to give us 2, negative 4, that's going to give us negative 8, that's going to give us negative 21, which gives us negative 42, and you get 0. Bingo, we got that. Okay, that's what we want. And remember, this was cubic, this reduces to quadratic, so now you have x squared minus 4x minus 21, you set it equal to 0. And you can solve this by factoring, for example. This actually factors very nicely as x minus 7 times x plus 3. And we're going to get 7, and we're going to get negative 3. So our solutions are 2, 7, and negative 3. You can write them in any order, does not make a difference. I do want to point out one thing. This is a cubic equation. We expect 3 solutions. We have 3 solutions. All of them are rational numbers, and every single one of them is on that list. Negative 3 is here, 7 is here, and 2 is here. Okay? So that's how it works. And we got one more example. So here our leading coefficient is 2, not 1, which means we're going to have to do 12 over 2 and set up all possible factors. So the factors of 12 are plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. divided by plus minus 1 plus minus 2. We take all possible combinations here, which is going to be plus or minus 1, that's 1 over 1. 1 over 2 is plus minus 1 half. 2 over 1 is plus or minus 2. 2 over 2 is 1, we got that. 3 over 1 plus or minus 3. 3 over 2 is plus or minus 3 halves. 4 over 1 plus or minus 4. 4 over 2 is 2, we have that. 6 over 1 plus or minus 6. 6 over 2 is 3, we have that. 12 over 1 is plus or minus 12. 12 over 2 is 6, we have that. These are all possible rational zeros. And just like the previous problem, you don't really know where to start. You can pick a number, and let's say we decide to try a 1 again as our... Well, actually, before I do that, let me point out one important thing here. If you look very carefully at this polynomial, all you have here is positive signs. So think about this. If you pick a positive number for x, you are going to get positive plus positive plus positive plus positive. Doesn't matter what number you pick. It's not going to be possible for you to get 0 here, which means the only possible way how you can get 0 here is if you pick a negative number. It is very helpful to look very carefully at your polynomial before you try numbers, because sometimes you have polynomials with all zeros and then it's not going to work. So we know we don't need to try 1 or 1/2. None of these positive numbers we're going to try because it's not possible for them to work. So what can we try? Let's try negative 1. Now, the challenge that we have here is going to be that this is a 4th degree, which means we can have as many as 4, and I need to try it. So this is 2, that's negative 2, that's 9, it's negative 9, there is 17, negative 17, that's 12, negative 12, 0. Excellent. So x equals negative 1 is going to be one number. Okay. I don't have a lot of room here to play, so you can continue trying numbers. The only other rational number that's going to work from this list is going to be negative 3 halves. Okay. You do need to keep trying. Unfortunately, well, for you, I have the luxury of knowing what the correct answer is, but if you don't, you just have to keep trying numbers, but at least you cut this choice of possibilities in half by realizing that positive numbers don't work here. So, and remember, we're using the reduced polynomial, so 2, 9, 17, 12. So what do we have here? That's 2, multiply this, that's negative 3, that is 6, negative 3 halves times 6, that's negative 9, 17 minus 9 is going to give us 8, negative 3 halves times 8 is going to be negative 12, and we have 0. Okay, so now we reduce that to, oh, one thing I want to remind you, since this is a fraction here, well, it doesn't really matter here. Here's what we get. We have 2x squared plus 6x plus 8 equals 0. We can divide by 2. This gives us x squared plus 3x plus 4 equals 0. And what we can do is we can factor it. No, this one does not factor, right? Because you don't have two numbers that multiply to give you 4 and add to give you 3. So since it does not factor, you are not going to have any more rational zeros. No more rational zeros. You can try to solve this quadratic equation. It will give you imaginary solutions here. It's going to give you something with I, but even if it wasn't imaginary, even if it was positive, it's still not something that factors, which means there are no more rational zeros. So the only two rational zeros are going to be negative 1 and negative 3 halves. There will be another lesson on finding all zeros, and then you can actually solve this equation and have more. But as far as finding rational zeros, this is all there is to it. And I hope this helps.